Okay, this video is about the recording for corrections for experiment 1. So in experiment 1, the aim of the experiment is to determine the concentration of a solution of hydrochloric acid. So as explained before in the practical, alright, FB1 provided is too concentrated. Alright, as a result, there is a need for us to do a dilution of FB1 before we do a direct titration with FB2, the sodium hydroxide. Okay, so the preliminary investigation was done, right, and discussed early on in the lab session. Okay, so in this case, we add 10 drops of FB1 in the test tube, and then we use screen-meter orange indicator. We quick recap on the color change. Alright, so screen-meter orange indicator, red, then to violet, or red when it's acidic. Violet is when it's just before endpoint, and then gray is where it's at its endpoint, and if you are past the endpoint, when you go to the basic region, the screen-meter orange turns green. Alright, so it's with the understanding, alright, then we use a dropper to investigate on how many drops of FB2 is required to reach endpoint. Alright, so 90 drops was required. So based on the proportion of 10 drops to 90 drops, the volume ratio, alright, the volume ratio is 1:9. And since NaOH reacts with HCl in a 1:1 ratio, alright, so if we are used 25 cm of FB1, which is HCl, alright, and therefore the amount of FB2 expected, which is the NaOH, I'll need 25 times 90/10, or 9, and therefore I get 225 cm3. Alright, so take note of the units, alright. Okay, so that's part A, and in this case, I'd like to reiterate part 3 again. So, why is FB1 unsuitable for use in titration directly? Alright, because the titer value. So what's the titer value? The titer value basically refers to the volume of titron. Alright, in this case, the titron will be FB2. Alright, FB2 is the one in the burette. So the titron is known as the solution in the burette. Okay, so titron, I repeat again, is the solution in the burette. Titer values is the results of your titration. That means the volume, alright, that you obtain from a titration. Okay, it's too large and therefore it's not in the optimum range. So this concept of optimum range was something that I discussed during the practical. Typically for titration, the optimum range of a titration is between 20 to 30 cm3. Alright, take note the precision of the burette is to 2 dp, so 20.00 to 30.00 cm3. The question is why? Okay, so it's a balancing act between minimizing percentage error. So what's percentage error? I will elaborate in a short while. As well as to minimize the need to refill burette for each one of the titration. Okay, so let me explain the part about refilling burette. So if a titration is between 20 to 30, alright, as a result, the subsequent run for your titration, alright, you don't have to really top up your burette again. Alright, so you don't have to refill your burette for each run of a titration. So the question is, why don't we then plan for a titration to have a 10 cm3 or 15 cm3? Alright, that's because with every instrument, alright, there's some degree of uncertainty that comes in measurement. So for example, if you're measuring a volume or taking a burette reading, alright, if it shows 0.10, alright, the error itself will be the smallest division. Alright, so it can be either 0.20 or 0.00. So it as a plus minus 0.10 cm3 uncertainty when you do a measurement. So if given this, alright, if you calculate percentage error is defined as the uncertainty divided by the absolute value. Alright, so if I use a larger absolute value, the percentage error therefore becomes smaller. Alright, so if you want more information on percentage error, can you please read your lab manual, alright, under the section of percentage error, error analysis. Alright, so it's a balancing act. Alright, we don't want it to be too large. Although when you have a very large titer value, the percentage error does decrease, but it will require us to refill burette every single run. Alright, you also don't want to be too small because the percentage error therefore becomes significant. Alright, so that's the part of the optimal range. Alright, but the main reason is we do not want to refill burette for each run because FP1 is just too concentrated, and as a result, it needs to be diluted. Okay, so that's the explanation for part 3 in full. So as a result, in part B, we will therefore have to prepare a diluted solution using a volumetric flask. Alright, so we mentioned before how to use a volumetric flask. So a volumetric flask is, it looks something like this, right? Remember, we will fill pipette in certain quantity and then we top up to the mark, right? You recall, we top up to the mark, right? And then we invert the volumetric flask a few times to homogenize the solution, alright? So in this case, we need to know how much FB1 was added, and this was when we took from your communal burettes, alright? So for those in 413, alright, many of you miss having your data 413, 303, 413 and 303 similarly, or you forgot to record your data for table 1.1. As a result, your entire experiment becomes void because you do not know how much FB1 was used to prepare FB3. Alright, so why do we label it as FB3? Because FB3 is a diluted solution. So in this case, what am I saying? I'm using 24.50 cm cube of FB1 to prepare 250 cm cube of FB3. Alright, this is important info that you need to take note, because this provides the context for us to find the concentration of FB1 later on. Alright, so basically you can see this process is a dilution. Alright, so you have a concentration of FB1 multiplied by the volume of FB1 you use will be equals to the concentration of FB3 multiplied by the volume of FB3, which is in this case 250, because you are topping up with water 250 cm cube. Alright, so 250 over 1000. Okay, and so far, so you need to apply this later on to find the value of the concentration of FB1. And then we move on to the titration using screen without orange indicator. So your burette is filled with FB2. Is it necessary to rinse the burette with little FB2? Yes. Why? Because to prevent pre-dilution of FB2. Right, the residual water from the washing will dilute your FB2 if you pour into your burette directly, alright, without rinsing the burette with FB2. So similarly, alright, it's also necessary for you to rinse the pipette with FB3 because you do not want to pre-dilute FB3 before transferring to a conical flask. Alright, this will result in lesser number of moles of FB3, alright, in the conical flask, and therefore affect your accuracy of your titration. So a few drops of screen without indicator, typically, alright, to consistent size, alright, the color change, alright, so it's best if you use about 2 to 3 drops, alright, so a rough gauge, as I mentioned to you, use 3 drops throughout, okay. So you run until the endpoint, and I think you guys are aware of the color change, okay. So you're supposed to record your titration results, and take note, this concept of consistent titer values, alright. I know that in O levels, your concept of consistent titer values can be within plus minus 0.10 cm cube of each other. But in A levels, this is a must, within plus minus 0.10 cm cube of each other. In other words, example, if I have 24.20 and 24.00, these are not consistent titer values. And what's the corrective actions? You'll need to do your third titration, alright, and fourth if necessary, so and so forth, until you get consistent titer values, alright. So the question is, sure, if I have 24.10 and 24.00, do I need to do a third one? You do need to, because these two are therefore consistent because they are within plus minus 0.1 of each other. Okay? So these values that I've obtained are ready for illustration purpose. The values here depends on how much FB1 you use. Okay, so these are my values. You can see that there is no need to top up your burette to 0.00 for every single run of your titration. Alright, all you need to do is to note your initial and your final, and then you use your final minus initial. Again, your final should be larger than your initial, because, alright, it makes sense, right? Your burette reading will be of a higher level, which means a smaller number. Alright, as you titrate down, as the solution level goes down, it will register a larger value. So please make sure you record your data correctly in the respective columns. Alright, subsequently, you guys will need to present your own table. Alright, so make sure the headings are there, as well as the units. Again, I want to reiterate the part about the headers. For burette, it's called burette reading, not burette volume. Alright, because the burette doesn't change its volume before and after titration. So it should be a reading and not a volume. So as with all burette readings and titer values, because of the precision of your instrument, your burette, all readings should be up to 2 dp, ending with 0 or 5. Alright, so these were all text boxes that we have indicated. Again, if your attention to details is there, alright, you should be looking at this and checking your data. Alright, you shouldn't be being fought, alright, for missing out details like this. Okay. Then, last but not least, we choose titer values that are within plus minus 0.10 and we indicate with a tick below the values. Now, this will show clearly to the examiner which are the values you choose for titration. Okay. So for part 1, alright, from our titration results, obtain a suitable volume of FP2 to be used in the calculation. So 20.90, 20.85. As a result, if you were to key in the calculator, you should get 20.875. Do I use 20.875? Nope, I'll round to 2 dp. Okay, your average volume should have to be rounded correctly to 2 dp. Alright, it's quite sad that some of you can't even round off the volume to the correct 2 dp. Alright, and together with the units. Okay, so let's take a look at schematics because some of you are struggling with the calculation and this is really appalling. Alright, you're using 24.50 cm3 of FB1 of don't know what concentration. That's our aim, right? If you recall, that's our aim. We dilute to 250 cm3 of FB3. So the concept of C1V1 equals to C2V2 has to be applied here. And then 20.88 cm3, alright, as calculated from the earlier part, was used of NaOH was used to against 25 cm3. So in this case, from 250 to 25 cm3, there's a concept of scaling. Alright, so we need to do portion. Alright. Okay, so we're supposed to calculate the amount of sodium hydroxide in the volume of FP2 required to react with the hydrochloric acid. So the question is amount of sodium hydroxide. And this is really quite frustrating. Alright, I have some of you who use mass over molar mass, which is not applicable here because you have a solution. A solution is not even a solid sample. How can you use mass over mass? Next, I have people who ridiculously use molar volume. Alright, molar volume 24 appearing in the context of this titration. Where are the gases? Alright, so again, please sort out your thoughts, understand the context of what you're doing. Alright, these fundamental mistakes are not to be carried out in this context of this titration. How can you have a gas in this titration? Alright, really? Alright, and we have completed more concept tutorial largely before we started this titration. Okay, so amount of NaOH basically is a concept of C times V. You have a solution, you use this volume, 20.8, convert to dm cube, multiply by the concentration of 0.1, you get the number of moles. 2.09 times 10 to the power of minus 3. Alright, was this the amount of NaOH? Yes, because this was the amount that used to react fully with the 25 cm3. Okay, let's take a look at part 3 then. Again, answer to 3SF. In this case, I express it in standard notation. Then in part 3, we're supposed to calculate the amount of HCl in 250 cm3. Okay, so this is the NaOH that reacted with 25.0 cm3 of FB3. So we are supposed to find the amount of HCl present in 250. So because NaOH and HCl reacts in a 1:1 ratio, this mole ratio needs to be stated. Alright, so the examiner can see how NaOH relates to HCl. So the amount of HCl present in 25 cm3, you can see it's the same value as what you've calculated from part 2. Alright, because you only use 25 cm3 of FB3 for the titration. To find 250 cm3, you therefore need to do a scaling. Right, you need to do a scaling. How to do scaling? Portion of 25, scale up to 250. You take the whole of 250 divided by the portion 25. You multiply by the number of moles, you get the number of moles present in 250 cm3. Okay, that's part 3. And in part 4, the last part, you're supposed to calculate concentration in the original FB1 solution. Okay, so this is the number of moles in 250 cm3 of FB3. Recall, in my context of my titration, I used 24.50 cm3 FB1 and I dilute it to 250 cm3 of FB3. The question is, what concept can I apply here? I can apply my C1V1 equals to C2V2. In this case, C2V2, we have the number of moles. This is the number of moles of C2V2 because the number of moles of HCl. Because the number of moles of HCl before and after dilution in FP1 and FP3 should be the same. Alright, so in this case, we know what's our C2V2, which is number of moles of HCl, 2.09 times 10 to the power minus 2. We know our volume 1 because it's 24.50 cm cube over 1000 converted to dm cube. Alright, and that's what I do over here. Alright, your C2V2 divided by your V1, and you get your C1. Alright, 0.853 mole per dm cube. Okay, some of you get a value that's somewhat different from this because of the accuracy of your titration, or accuracy in terms of your preparation of solution. Okay, in part D was something that I went through with you guys. So two students misread the instructions while performing titration. So what happens? In student A, they rinse the burette with DI water but not FP2 before filling it up. Alright, you're supposed to predict with reasoning how it affects his titration results, titer values. So in this case, his titer values will be higher than expected. Why so? Okay, as I explained, because the titrant, notice I use the word titrant. Titrant refers to the solution. Titer values refers to the experimental results. So you need to know the difference between titer and titrant. They are different. Alright, so in context, you need to know when to use titer, when to use titrant. Alright, why is it diluted? Because of the residual water present in the burette. So, as a result, because it's more dilute, to bring about the same number of moles for the reach endpoint for titration, we need a larger volume. Alright, take note, it's not amount, because the amount remains the same. Alright, the amount of NaOH required to reach endpoint is still the same, but because the concentration is lower, therefore your volume needs to be higher. Okay, that's your D part 1. Okay, in D part 2, okay, what happens when the student rinse the conical flask with FP3? Alright, and then before introducing 25 cm of FP3. So again, titer values will be higher than expected. Why? So there will be larger volume of FP3. Why so? Because you have rinsed it, there's some residual FP3 in the conical flask. This brings about greater amount of HCl, not greater concentration, but you just have more moles of HCl because of the larger volume of FP3. So if you have larger amount of FHCl, you definitely need a larger amount of NaOH to reach endpoint. So more moles of NaOH is required, and therefore you need a larger volume of FP2, and this results in a higher titer value. Okay, but there's no change in the concentration. Okay, some more common misconception and some unclear explanation. Alright, surprising that when I gave you time to discuss this question, and I showed you guys the corrections for this, and some of you can copy wrongly. Alright, so FP3 is the label of a solution, not a chemical name. So please use number of moles of HCl, not number of moles of FP3. Alright, do not just say more, specify whether it's more volume or more moles. Okay, there's a preliminary discussion for this. So I've explained, so in case you guys are wondering, how do I decide to choose 24 to 25 cm cube? Okay, the solutions is over here. Because as I said, an optimum titration value is about 20 to 30. So based on that, if I substitute in 25 cm cube, alright, then I will be able to work out a value of what's the optimum range. Okay, so I'll leave these solutions up here. You can pause this video to copy down the solution if you want to look at the what's the discussion question. Okay, so by considering answer in A, the volume of FB1 chosen for direction, determine the expected titer values. Alright, so expected titer value is about 22. Okay. So over here again is a screw metal orange indicator color change. We have red, alright, at the start of titration. This is given the context that it's acidic because you have your HCl present in the conical flask. Okay, so take note the starting color may change depending on what's in the conical flask. Okay, typical color transition. Alright, if you start from acid, it will become violet, and then after that you reach grey at the end point. So if you start from green, alright, if you start off from the base in the conical flask, you start from green to go to grey. Alright, so green to grey. Alright, so you must be clear what's in the conical flask and what's therefore the color change for screen metal orange. Okay, with that I'm done for the corrections. I just want to alert you guys to page 27 of lab manual. These are the checklists for how you present your data for VA experiment. Can you please take a look at page 27 of the lab manual and make sure these are always adhered to when you do your presentation of data for VA experiments. Okay, with that, that's it for our experiment.